So what is the scope of thermodynamics? What thermodynamics helps us about? Like what is the need of thermodynamics? It helps us to understand the feasibility of reaction, whether a reaction is going to like go in the forward direction or not. Suppose you are doing a reaction and you have mixed something and you are hoping to get a new compound, a product basically. Suppose you are hoping to make tea and you have transferred your milk, sugar and tea leaves, right? Hoping to get tea.
Yeah.
But if that reaction is not thermodynamically favored, then you will not get your tea. So what is helping us to understand whether we are going to get our tea, that mean product, is thermodynamics. It tells us about the feasibility of the reaction, whether reaction is going to proceed or not.
Okay.
Okay. It also helps us to calculate the energy changes if the reaction does take place. Suppose the reaction that you are hoping is going in the forward direction, but how much energy change does it like uh, showing basically you can say, right? Is it an exothermic reaction or is it an endothermic reaction? You're getting what I'm trying to say? What tells
Yeah,
us whether the reaction?
exothermic reaction, right?
Hmm. Okay, what else? Calculate the extent at which a chemical reaction process. The extent, like whether a reaction is going at 70 degrees, 70%, 60%, right? The extent is also talked about while we are talking in terms of thermodynamics. So what are the limitations of thermodynamics? Thermodynamics limitations are these basically. It is only applicable on macroscopic system, not to microscopic. I told you the reason behind it. What was the reason why we are only
Yeah.
applying thermodynamics on macroscopic particles? What will happen
Because
if
it's too complex.
hmm,
You cannot see there are like millions of atoms, and you cannot, it's gonna be complex to measure the energy.
So we have a special category of thermodynamics for that. We call that statistical thermodynamics. And that thermodynamics is pretty complicated, right? So you don't have to
Yeah.
even think about it. You have your simple plain old thermodynamics. So I told you, if you are supplying 100 joules of energy to a system E, then you can say that the whole system, suppose the system is containing water, that the whole water is experiencing 100 joules of energy. But can we say that about a single water molecule as well? No, because inside this water, there might be billions of water molecules. How can you comment about the like how much a single water molecule is absorbing out of this 100 joules of energy, right? So it would be very complicated. Okay.
Yeah.
Thermodynamics tells us about the speed of the, oh, sorry. Thermodynamics cannot tell us about the speed of the reaction. Thermodynamic will only tell you whether the reaction is feasible or not. It will tell you the reaction is going to proceed, right? It will tell you
Yeah.
that you can make your tea, but how long is it going to take? Thermodynamics don't talk about it. It might take 5 minutes, it might take 10 minutes, it might take a day, it might take a year. Thermodynamics has no concern about the time or speed of the reaction. To understand the kinetics, that means speed, we have an entirely different branch of chemistry. We call it chemical kinetics, right? In your packed food, you must have one like whenever you are opening the chips packet, there is some gas inside it, right? What is that gas doing basically? It is making its half-life longer so that your food that is packed can survive for longer period of time. Otherwise, if you are just letting it out in mo atmosphere, it might get absorbed moisture and it will, what you call that, the खराब होना, food का खराब होना. What do you call that?
Which one?
The food that it might went bad. What is the specific term that we use while we are talking in terms of food? I know the generic term bad, but what we call it while we are specifically targeting food? It's English. Uh,
Um, or
tell me.
rancid.
Rancid. Okay. I have no idea about it. So you can say that. So
Or mold.
thermodynamics, hmm, bread, right? Okay.
Yeah.
So what is the second limitation of thermodynamics? Tell me.
That it doesn't tell how, sorry, it doesn't tell how long it will take.
Hmm.
How
It will tell
long?
you it is going to take some time, but how long? Thermodynamics has no concern about it. Okay.
Yeah,
Suppose for this example, you are reacting A plus B and you are getting C. Thermodynamics can tell A plus B will give you C. If you are mixing milk with sugar plus tea leaves, thermodynamics can say you are going to get your tea, but it won't tell you how long it is it going to take, right? Or what is the speed of the
yeah.
reaction. For example, this H2 plus O2, right? Okay.
Mhm.
Then we talked about system, boundary, and surrounding. So can you give me a brief about it? Like I have already taught you this. So can you tell me what is system, what is surrounding, and what is the other thing, boundary?
Okay, just a minute, just a minute, just a minute, just a minute. Okay, system. System
Mhm.
is the the system, the things that is the major things. The boundary is that separates the system from the surrounding,
Mm.
and surrounding is everything but the system and the boundary.
Okay, so you have a cup of tea. Tell me what is your
Mhm.
system, what is the surrounding, and what is your
Okay,
boundary?
cup of tea. Tea is the system.
Mm.
Cup is the boundary, and everything that is not a cup and not a tea is the surrounding.
Good, good. So you remember it. So let us talk about heterogeneous and homogeneous system as well. What is an homogeneous and heterogeneous system? Homogeneous, as the name suggests, homogeneous means uniform composition, right? So whenever
Yeah,
you have a system where you are not able to separate the two systems, suppose you are having a mixture of gases, you won't be able to separate the gases because the intermolecular forces are very weak. You cannot control the molecules of gases, right? They will automatically be,
yeah,
what you call it, mixed together inside a container, right?
yeah.
But the heterogeneous system is the one where you can separate or you can differentiate between the two phases, right? So in your
Yes,
thermodynamics, the most cases that you are going to come across are going to be about hetero system, right? So let us move ahead.
yeah.
Types of thermodynamic systems. We have three types, right? Open, closed, and isolated system. So can you tell me with simple examples what are open, closed, and isolated system?
Open, close, and okay. Open is that where the matter can escape to the
Hmm.
surrounding.
Only matter.
Okay, I'll just tell you this. Open is where there's an open container and the system is exposed to the surrounding. Um, exposed to the surrounding.
Okay, to make
So,
things more simpler, now you can have simple examples like you can take a cup of tea, right? Take those
okay,
kind of
cup of
examples
tea.
to make because
Okay,
the
cup of tea is an example of a open system.
okay,
Um, so as and the tea is exposed to the surrounding, correct?
hmm,
So
because the cup is
in
not
that,
closed, right?
yeah, the cup is not closed. So
Hmm,
in this case, matter matter exchanges exchanges
hmm,
and energy
as
also
well,
exchanges.
right? Because the initially your cup might be hot, but as you have
Yeah,
left it in the surrounding, then it might get
as the
cold because
steam escapes to the
hmm,
surrounding and the
hmm,
tea gets cold.
good, good. What about closed system?
Now closed.
Hmm,
Just a good example is when a lid is closed over the cup of tea,
good.
where the matter is not exchanged, the steam of the tea doesn't escape,
Mm-hmm.
but it still gets cold. It still gets cold.
Good,
So
good.
energy exchanges.
Good.
But isolated system, a good example is flask, hydro flask.
Good.
Um, in hydro flask, the matter doesn't escape and the temperature doesn't changes. It's always constant. So thereby, matter doesn't exchange and energy doesn't exchange.
Good. So do you have any doubts regarding these two topics? I hope not.
No.
So let us move ahead. So we have talked about this term boundary, right? So we have sort of two or three types of boundaries. The one which is adiabatic is where no heat exchange is taking place. So if your boundary is adiabatic boundary, then matter as well as your energy won't exchange from and to the surrounding, to the system and surrounding, right? But if you
Yeah.
are talking about diathermal boundary, then your matter won't be able to exchange, but energy will do. And the boundary,
Okay.
you can consider it as a piston. Suppose, I think you told me in the previous class, you know what piston is. The piston is something that is movable, right?
Yeah.
So it is another sort of boundary, basically. Okay. So now, as we talked about, like the thermodynamics is only done for the macroscopic substances, macroscopic things, right? If you have something that you can see with your eyes, suppose anything, your laptop, your phone, there we can apply thermodynamics, right? So we should know
Yeah.
what are macroscopic properties. So macroscopic properties are what?
Macroscopic properties are the things that we can see by our own naked eyes.
Properties, I'm talking
Uh,
in terms of properties.
oh, okay, okay, okay. Um, um, it can be seen. There is a volume. There's like a meters, like measurements.
Mhm.
Um, then I guess that's it.
Okay. Okay. So the macroscopic properties are basically pressure, volume, temperature, density, composition, surface tension, etc. Because you are able to tell about it by just measuring it. So
Yeah.
suppose
What's
uh,
T
temperature, T for temperature,
and P?
P is pressure, V is volume. Okay,
V is volume. P is pressure. Okay,
pressure.
fine.
Yeah. Okay. So basically, macroscopic molecules, macroscopic substances are those substances where you are usually observing a large number of particles combined together, right? So how are
Mm-hmm.
we going to relate it with the states of matter? I told you very like in detail manner in the last class how state of matter depends on the macroscopic property. Would you want to, would you like to explain it? Like, do you remember anything from the previous class what I told you?
Mm, I no, I don't remember. Can you explain?
Sure. See, when macroscopic properties of a system have definite value, the system is said to be in a definite state. What do we mean by this? Suppose you have a container, right? And you have
Mm-hmm.
covered it with a lid that is working as a boundary, right?
Mm-hmm.
So at a particular period of time, that container is going to have a specific pressure, specific volume, specific temperature, and the number of particles that are present in that substance is also going to be specific, right?
Yeah,
So we can say the state of the system is defined. It has a definite state.
yeah,
But what if you are changing its macroscopic properties? Suppose you are putting some heat, you are changing its temperature. As the temperature is changing, the volume will also change. As the volume is changing, the
yeah,
pressure will also change. And due to all this, the number of molecules will also change. So when you have started heating your container, then what you can say, the macroscopic properties is changing, right?
yeah,
So you can say the state of your macroscopic particle or system is changing. So this is basically your state of matter. State A changes from B due to change in macroscopic particle. And these macroscopic properties are called state variable or state parameters. These macroscopic properties define the state of an system. So I would request you to please read it and try to remember it, because this is the basics of this thermodynamics, and we are going to use these concepts as we will be moving ahead. So please give it a read. And if you have still any doubt regarding this topic, then please let me know.
Okay.
Right?
Okay. Okay then.
Just give me a second. So let us move ahead. So now we are at equilibrium. What is an equilibrium? An isolated system is an equilibrium when its macroscopic properties remains constant. So when you are going to say that your system has achieved equilibrium, when its macroscopic properties are not changing with time. For example, you have a system and its temperature or pressure or volume or the macroscopic properties have remained constant for a period of time. So what you will call it? That your system has achieved equilibrium, because from now on, the macroscopic properties are not changing. So the system is an equilibrium. Okay. Oh, I haven't added the things on the PDF. Yeah. Hmm. Okay, so let me tell you. We talked about three types of equilibrium.
Yeah.
Uh, the first one was mechanical equilibrium.
Thermodynamic equilibrium.
Hmm.
Uh,
Thermodynamic
th
equilibrium consists of three types of equilibrium.
thermo equilibrium, mechanical equilibrium, and there was one to uh what was the last one? Something to do with molecule, molar, I think.
See. You are correct in the terms, but I think you are not calling the name right. See, first one was mechanical equilibrium. Second one
Yeah,
was,
that's what
you called it,
thermo.
uh, the first one was thermo, the second one was mechanical, and the last one was, I think what was where we were talking about the number of moles. The number of moles remains constant, right?
Molar, right?
So something like that. So I can do one thing. Let me show you. And before like assigning you homework, I will do one thing. I will update this PDF so you can share that with it.
Oh yeah, there were. I thought you connected those
Hmm.
PDF.
I forgot. I forgot. I will update it before the class, like before assigning homework. Hmm. I think it was around here. You are going for like, what are your future plans? Like, are you going for engineering or do you have something specific in mind?
Apparently the whole family wants me to go for engineer, so yeah, I'm going for engineer.
Uh, good luck at that. Okay, so thermodynamic equilibrium. When you are going to say your system has achieved thermodynamic equilibrium, you will say
Mm-hmm.
when it has thermal equilibrium plus mechanical equilibrium and chemical equilibrium. If your system has these three equilibrium, then you can collectively call it thermodynamic equilibrium. As you already mentioned, what is thermal equilibrium? When no further heat exchange. What is mechanical? When the movement of piston, suppose you were moving your piston downwards and you were applying some external pressure on it. Once your external pressure reaches internal pressure, suppose you are compressing gas, and while you are compressing gas, gas molecules are coming closer to each other. And when they are coming closer to each other, there is an increase in repulsion. So at some point, you won't be able to push your piston any further. So that point, you will call it that you have achieved your mechanical equilibrium, because now the gas particles are uh,
I thought that was just like the example. What's the definition of mechanical equilibrium?
see, the definition would be when external pressure is equal to internal pressure in a system. Pressure, basically.
Okay.
In chemical, then no exchange of moles, right? When system
So
achieves,
external pressure is equal to internal pressure.
yeah, you can say it like simply, right?
Thermal is just the exchange of temperature or energy,
Heat. Thermal is heat, as the name suggests,
heat
heat.
exchange.
Yeah, right. So when system achieve all the above three equilibrium, then the system is in thermodynamic equilibrium. If you are missing any one of the equilibrium, then you cannot say that your system has achieved thermodynamic equilibrium. For thermodynamic
Yeah.
terms, you have to see whether these three conditions are satisfied or not. So let us move ahead. This one you should remember, because I think we took several examples to understand it. What are extensive and what are intensive properties?
Mhm.
This is the last topic, I think, from the previous class. After it, we will continue with the fresh topic. So please
Okay.
let me know whether you remember this or not.
Okay. Yeah, I remember.
Mm.
But please give me one example.
For example, see,
I know
as
the
the
definition though.
see the what? Tell me the definition first, then I will tell
Okay, the
you.
property that of the system that depends on the bulkiness and the shape.
Not bulkiness, the bulk. By bulk,
The
we
bulk.
mean how much amount present.
And intensive is just opposite of extensive.
Suppose you have a wire, right?
Yeah.
And we have studied about the resistance. What is resistance?
Which one? Oh, that example. Yeah, I remember.
Tell me that.
The long wire, but has less radius, has more resistance, and the wire that has a lot of radius has more. I mean, less resistance.
To put it simply, you can say as whenever the current is moving through a wire, it will lose some of its current due to resistance. Resistance due to the
Yeah.
wire, right? Voltage, basically, it will lose some voltage. And that is the reason you are not able to use your cells for, suppose, eternity. Your cell life is a specific time, right? Whenever you are buying a
Yeah.
cell, it will run out after some time. So that is because of
Yeah.
resistance. So whenever you have a big wire, a long wire, that the resistance will be higher because your voltage has to travel through a long distance. As the wire is longer, as the wire is longer, there is more resistance. But what about resistivity? Resistivity is just a property, but resistance is something that depends on the bulk. So resistance is what? Extensive, and resistivity is intensive. For example,
Yeah.
resistivity basically is the property. Suppose your wood. Wood is resistive or not? Can you pass electricity through wood? No.
Oh.
So it's just a property.
Yeah.
I took another example about glass. You
Glass.
remember?
Oh yeah, the glass slab. Yes.
Mm-hmm.
Um. Yeah. I have said that. It is an no, wait, just a minute. It is an extensive property because it depends on the reflective index depends on the density of the glass. Um, am I doing this correct? The glass depends on in re-
See, see, see.
reflective
Yes,
index.
see, see. Whenever you are taking specific example of refractive index, right?
Yeah.
Or do you want to take density as well? So let us take us both. Suppose if you are talking about refractive index, you have a whole glass slab, right?
Hmm.
The refractive index is going to be the same if you cut out a small piece of your glass slab, and if you compare the refractive index of both the one where from where you have cut the small piece and the small piece, then both will have the same refractive index, right? So this is an
Yeah.
intrinsic property because it does not depend on the bulk. Same for the density. Is it clear
Okay.
now? Do you need some more examples?
So, say that again. Like, what does it depend on, though? I mean,
See, see,
yeah, it's intensive, but what does it depend on?
it does not depend on the bulk. See, if you
Yeah,
have a
but
glass slab, if you have a glass slab, you took a small piece out of it
mhm.
and you checked its density.
Oh, okay, okay, okay.
So the
It's the same thing.
density of your small piece and the density of the whole thing is same. Why?
Yeah,
Because suppose the density is basically mass per unit volume or not.
yeah,
If you are talking about the whole glass slab, then you can this is just an hypothetical value. If your mass of your whole glass slab is 10 and volume is 10, then the density is 1. But if you are taking a small piece out of it, it would acquire a specific type of mass and volume so that the density is again coming out as 1. Suppose now the mass is 1, then volume will also be 1. So again the density is going to be same no matter if you are taking the whole piece or a small piece.
yeah.
Is it making sense or do we need to
Yes,
take
yes, yes. It does, it does.
and yeah, extensive is additive and intensive is non-additive. For example, suppose we are talking about mass. Mass is an extensive property. If you are
Yeah,
combining two masses, then it is going to add up. Suppose I am
yeah,
merging two things 50-50 kg, then it is
yeah. I
ultimately going.
understand, I understand, I understand, I understand.
But 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 what about density? Suppose you took a piece from your whole glass slab and now you are thinking of attaching it back.
It's the same thing as a glass lab example.
Uh, if you are trying to attach it back, suppose you have this small glass slab and this is your hole, the thing where you cut it. Now, after
Mhm.
studying it, you are thinking I will attach it back and my density will add up. No, it is not going to work like that because the density is still going to be same. If the density of that small piece
Yeah,
is 1, the other one is going to be 1. It is not going to become 2. So it is non-additive. All right.
yeah.
So let us move ahead with our chapter then. Now we are going,
Can I say the density, but with different example?
you are talking about what? Like you can take several example for intensive property. But
I know.
what are you referring? Like how density? Why do you need
Water.
example? Density of water? Yeah, you can go say that. The density is going to be same. The density of pure
Yeah,
water is 1.
yeah. And if it doesn't change if we add more water,
That's
it's
a
gonna
good
be the
guess.
same thing.
Good, good, good. Your explanation is correct. Right. So let
Yeah.
us move ahead now. What do we have here? Ah, So now thermodynamic processes. We talked about what what is a thermodynamic system. Now let us talk about thermodynamic process. When a thermodynamic system changes from one state to another, the operation is called thermodynamic process, right? So we have 5 type of thermodynamic processes. These are pretty simple. The actual like tiresome thing that is going to come from this chapter, you are going to face it after like in the next class, I think, but today's class is going to be simple. So the first one is isothermal process. Have you heard about these terms like isothermal,
Just
isochoric?
1 minute, just 1 minute, just 1 minute.
Mhm.
Let me just read with the definition real quick.
Sure, sure, sure.
because I don't know what I'm looking at.
Hmm.
Thermodynamic systems changes. What does thermodynamic system mean? Like the what does mean?
The thermodynamic system is the system what you are studying about. Suppose thermodynamics basically talks in terms of energy exchange, right? So whenever
Yeah,
you are studying a system and you are studying its change in energy, so you will call it
that's
thermodynamic system.
thermodynamic system. Okay, okay.
Okay.
And what does it mean if thermodynamic system changes from one state to another?
See, if your system initially had some specific amount of energy, after applying some sort of process on it, its energy state is changing. So you will say now your thermodynamic system is in another state. For example, the simplest example would be we talked about the state of the system, right? How the macroscopic
Yeah,
properties were defining the state of the system.
yeah,
If you are
yeah.
changing the state, macroscopic state, your system is also changing the state of the system. So it is just that.
Oh, okay, okay, okay. Yeah, I understood.
Okay, so try to go through the specific terms, isothermal, and then I will explain it. It won't take much time. It
There's
is
no
very
definition.
simple. It is the simplest or easiest thing I would say. It is even easier than the previous chapter. Try to just give it a read for 2 or 3 minutes, then it will make much more sense while I'll be explaining. Right? Meanwhile, I am going to uh, plug my charger.
What is it said? T is equal to unit.
P is equal to unit.
T.
PV is equal to nRT. Haven't you heard about this formula? It is pretty famous.
Which one? Which one?
PV is equal to nRT.
NRG.
nRT.
NRT. No, I don't know.
Okay, no worries.
NRT.
Okay, so are you done with the reading? Let us continue then.
Yeah, even though there's no definition, but yeah.
Oh, okay, okay. I haven't. Okay, yeah, 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 no worries. See, the simplest way is whenever you are performing a thermodynamic process, keeping your temperature constant, right? So you will call that
Yeah.
process isothermal process. Simple. When temperature is constant, the process is isothermal process. And if
Isothermal process. Okay.
and if temperature is constant, then the change in temperature is going to be what?
Zero.
T2 minus T1 is 0. Why? Because T2 is constant, T1 is constant, and if you are subtracting same thing, then you are going to get 0, right? So similarly, let us
Yeah.
talk about adiabatic process. See, this Q means heat, right?
Heat.
Uh, So if in your system you are keeping the heat constant, that means you are not allowing your system to exchange heat from the system to the surrounding, then you will call that process adiabatic process, right?
So heat is constant.
Yes, heat is constant.
Okay.
Suppose by constant, what do we mean? By
It's the same
constant,
thing.
no, it means you have specified. Suppose you are performing your process at a specific temperature. Let it be 25 degrees
It's
Celsius.
distinct.
It's specific, constant, right? It is not going to change.
Yeah.
Okay. So
That's yeah.
what about isochoric? Isochoric means now the volume is constant. Isobaric means now the pressure is constant.
Pressure is constant.
If something is constant, it is not going to change. If it is not going to change, then the change is going to be 0. That means delta T is 0. Delta TQ is 0, delta V is 0, delta T is 0. What are cyclic process? What do we mean by cyclic? Cyclic means we have,
Okay, okay, okay. That T is equal to constant. What that's what you wrote.
this is constant. What were you understanding? Like, however you,
Unit, I think. I thought it was unit or energy or something.
okay, now it should be clear. Cons. and the N means
Yeah,
constant.
that's fine. That's fine. That's fine. That's fine.
Now, what is cyclic process? Cyclic, we have always heard about it. Like whenever we are talking about cyclic process, we are coming back to the initial stage, right? If we are starting from A, when we are then we are coming back to it. So these type of process are called cyclic process. So in cyclic process, your del U, which is internal energy, and del H, which is enthalpy, is going to be zero. I think I'm sure like we haven't talked about the internal energy and enthalpy part right now. Okay, so
Okay.
for now, just keep it like the del U and del H is going to be zero. I will explain what is internal energy, what is enthalpy. Both are energy, but the energy exchange at some specific condition. Right? I will come to it later. For now,
So du and I mean, the delta H is equal to zero.
that means there is no change in internal energy, no change in enthalpy, right?
Ex Enthalpy, even though I don't know what that means, but yes.
See. Let
But
me give
what does
you.
H mean?
H means enthalpy. Let me tell you what is
Enthalpy.
enthalpy. Suppose you are performing an experiment, and you are observing some heat exchange, right? And
Mm-hmm.
the condition that you have applied, you have kept the pressure constant. While the pressure is constant and you are observing the change in heat, then you will call that change in heat enthalpy. At
Oh.
constant pressure,
How does it
the
happen though? The pressure is constant.
you can keep the pressure constant. Like we have instrument for that.
No, I
Atmospheric
know
pressure.
that. I know that, but how is heat changing? I mean, increasing if the pressure is constant? Are
It
they
just
heating it or
see
applying energy?
they might be applying energy or the system might be giving them energy by doing some chemical reaction. It can go both ways. But the thing is,
Mhm.
at constant pressure, whenever you are observing exchange in heat,
Exchange of heat, then it
then you
means
will call
enthalpy.
enthalpy. Enthalpy is nothing but energy. Enthalpy is basically change
Yeah.
in energy. To differentiate it with internal energy, we call it enthalpy. You will understand it. Let us reach that point. It will make it
Then
much more.
you,
U is internal
that
energy.
I understood.
Internal energy. Internal energy, you are keeping your volume constant now. Rather than putting the pressure,
Now my volume's constant,
and you are
but
observing
heat
the
is
difference.
changing.
So you will call that heat exchange
Internal
internal
energy.
energy. That's it. The naming is different, but the meaning, we are basically talking about change in energy, but we are giving them different names so that we can differentiate them, right?
Yep, I'm totally not gonna get confused between those.
You are going to get confused, right? So, are you clear with what are isothermal?
Yeah.
Okay, so in this adiabatic process, we are going to deal with this complicated, but still I will make it into something simpler for you. Poisson's ratio,
Okay.
right? So
What does
Poisson's
the symbol? What is that symbol?
gamma.
Gamma. Okay.
Okay, so this Poisson's ratio is something, suppose for simple, we write PV is equal to nRT. For ideal gases, right? We use PV is equal to nRT. But as here we are keeping the heat constant, we have a different thing. Here we will use this gamma, right? And this gamma is basically nothing but Cp by Cv. At the Cp/Cv, we will talk about it. And this gamma is basically Poisson's ratio, and it is always going to be greater than 1 because Cp is greater than Cv. This we will understand when we will be talking about the Poisson's thing, right? I have
Yeah.
attached it here so that you won't have to like like to keep things simpler. I have attached this here as
This calculation in this lesson.
well. You are talking about the numerical part.
Yeah.
We will deal with some numericals and derivations as well, right? So what are cyclic
Okay.
process? When a system is in a given state, goes through a number of different process and finally reaches to its initial state, the overall process is cyclic process. Suppose you started from your home, you went to school, you might uh, went to some other place with your friend, right? And then
Mm-hmm.
after wandering around whole day, you reach back at your home. So you are now back to your initial position. You started from your home and now you are back at your home. So this process
Okay.
is what? A cyclic process,
Okay.
right?
Okay.
So this is a very important graph. So what does it tells us about? Suppose this is your pressure, this is your volume. So if you are talking about isobaric, isobaric means pressure is constant. So your pressure is going to be a specific number, a constant, right? Suppose this is 10. So your pressure is going to remain 10. It is constant. Are you getting what
Yeah.
I'm trying to say?
Yeah.
So
Yeah.
for
Yeah. Yeah. Yeah.
pressure constant, that is specifically isobaric processes, the curve is looking like this. And for isochoric, what do we have for isochoric? Volume is constant, right? For isochoric, the volume is constant, so your graph, so your curve is going to look like this. A volume has a
Okay.
specific number, but for isothermal, the temperature is constant, right?
Yeah.
So your curve is going to look like this. As you are increasing the pressure, or you can say as you are increasing the volume, your pressure is decreasing. Can you relate it with simple examples? Suppose you have a container and you are doing what? You are applying some constant heat, right?
Mm-hmm.
As the volume of a container is increasing, the pressure will decrease or increase. You can simply think about it.
In
Suppose,
what?
suppose you have a 5 liter container
Mm-hmm.
and you have a 10-liter container and you are heating
Mm-hmm.
both the container with let us say 50 degrees Celsius, right?
Okay.
In which container the pressure will be more? The one with the lesser volume, the one with the higher volume. The thing
Hmm.
that you should keep in mind is the pressure is due to the gas particles. When the gas particles are compressed, they exert pressures. When are they compressed? When are they getting like compressed? When the system is small.
The high volume one, right?
The high volume one will have less pressure because
High
your gas
less
particles
pressure.
have the gas particles are free to move. They have more space to move around. They are not
Oh,
exerting that much pressure. Suppose we are sitting in a room, then the room is small. Then we are going to exert pressure to each other, and that will cause us to exert the pressure on the wall as well, because the room is
yeah.
small and we are exerting pressure everywhere. But on the other hand, as if the room is big, we can move around anywhere. So we are not exerting pressure onto each other as well as not to the wall
Okay,
as well.
okay, okay.
So as the volume is increasing, what is happening to the with the pressure?
If the volume is big, the pressure is small, and if
Hmm.
the volume is small, the pressure is big.
So is this yellow slope is making sense,
Yeah.
right?
Then, adiabatic and isothermal look same.
They are pretty same, but the dip is more in adiabatic. The adiabatic
How?
has, see, this gamma,
Mm-hmm.
we have the formula PV gamma is equal to constant. For this one, for this isothermal, we simply say PV is equal to constant, right?
Yeah.
But for this one, we have PV gamma is equal to constant. This gamma is the reason that explains this extra dip, this exponential dip, right? So
Yeah.
whenever you are talking about process isothermal versus adiabatic, you will observe more dip in pressure when you are increasing the volume, right?
Okay.
What, right?
Just 1 minute. For 1 minute, can you show the graph and the uh, you know,
This,
that part, the
mm,
processes.
yeah, please.
I just want to look them together for 1 minute.
Mm.
What does T mean again?
T is temperature.
And Q?
Q is heat.
What is the difference?
See, heat is see, whenever you are applying temperature, you are basically temperature is basically you can measure it, right? And
Hmm.
heat is related to exothermic or endothermic processes. But temperature is something like the measurement of the state of your, what you can say.
Temperature is measuring endothermic and exothermic, but heat
Heat
is
is
only exothermic.
no. Heat could be exothermic or endothermic. Try to understand it that way. Suppose you have a system, right? Am I visible?
Yeah.
Just give me a second. So, you have your system, right?
Mhm.
And you are suppose if it is an exothermic process, you will observe some amount of heat releasing from it, right?
Yeah.
Suppose you have placed a windmill, right? Windmill. That windmill, right? And if your process is exothermic, the heat which is evolved from the system would be able to rotate that wheel. So this is your heat which is releasing from the system. And if you're talking about the temperature, temperature is something which you are just keeping as a suppose uh, you are measuring your room temperature, right?
Yeah.
So that is temperature. But what is heat? If you are supplying heat in the form of, suppose you are burning your container, you have put uh, heat,
Oh, okay, okay.
that is heat.
Applying energy.
Applying energy, that is heat. But whenever you are measuring the temperature, that is your simple temperature, like 25 degrees Celsius,
Oh,
26
okay, okay.
degrees Celsius.
So heat is endothermic then.
Heat could be endothermic as well as exothermic. It will depend on the
Oh,
salt
yeah,
type
yeah,
of
yeah.
salt.
It can differ too because after some time it can release some heat.
Hmm. Right.
Hmm. Yeah.
While you are burning, suppose you have put your container, you are heating it.
What does gamma mean though?
Gamma is
That
just a
was
constant. You will
gamma
see.
is just a constant.
It is a Poisson's ratio. Suppose we will talk about it in details in the upcoming lecture. You don't have to think too much about it for now, right? It is just a constant that is associated
Okay.
with adiabatic process.
Yeah. So isothermic and adiabatic is temperature constant processes.
No, adiabatic is
So
heat constant. Adiabatic is heat constant, but your isothermal is
yeah,
temperature
yeah,
constant.
I know. But heat is also a temperature. So I'm just saying that both refers to like temperature or heat or energy.
So let me help you with this.
But
I'm
other
going
is
to
like macro properties like pressure and volume. So it's straight lines. Yeah,
let
I
me
can remember if I look at
no
it.
issue. Let me search for a better example so that you can understand better. Just give me a few seconds. Huh? Uh,
Yeah.
see, okay. Heat is simply a form of energy, right? Heat flows. How the heat flows? Whenever you are putting your, let us take our cup of tea back, right?
Yeah.
You have tea in your cup, right? You have left it for some time. What you are observing? The heat is flowing from your cup to the surrounding. Heat always
Yeah.
flows from hotter to cooler, right?
Cooler
Something like
area.
right. So it is heat. It is a form of energy. It is measured in joule or calories. So a simplest example would be when you heat water, right? Heat energy is
Uh-huh.
transferred from your flames to the water. This is heat. You are supplying heat to your water. But what is temperature? Temperature is simply how cold or how hot something is. It measures the
No,
kinetic
I
energy.
understood what temperature and
Hmm.
heat is. I understood that. I understood that.
Okay.
Were you
So,
just finding example for that only?
what else do we need? Like, do you have some specific doubt?
Nothing, nothing, nothing. No, 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 no.
Okay.
I
So,
just want to know how could I remember those names. Isobatic,
isothermal.
charic,
See,
isobatic
Isothermal, you are seeing this T. Isotherm.
temperature.
Therm means temperature, right?
Hmm.
Isobar. What
No,
is the,
thermal means heat, no?
you have to relate it here as temperature to learn it basically. Iso T, thermal means temperature.
Yeah.
Temperature is constant. For
Okay.
heat, you have adiabatic. Do you know the unit for pressure is bar as well? You can measure pressure in bar. 1 bar, 2 bar, 3 bar. Have you heard about the unit bar for temperature measuring? So, sorry,
For
for pressure measuring.
temperature?
No,
Oh,
no, pressure.
uh, pressure.
1 bar pressure, 5 bar pressure. Have you heard about it?
Yeah, I heard about it. Yeah.
So whenever you are hearing this term baric, isobaric, right? So bar means
Oh, okay, okay.
pressure, so pressure is constant. Thus, the last one is isochoric. So for choric, obviously the volume is left, so you will call it volume is constant.
Okay.
Thermal, temperature, baric, pressure, and the rest, the left one is choric, which is volume.
And adiabatic?
Adiabatic is basically heat,
Okay, but you didn't show cyclic process in the graph. Why?
because see, in cyclic process, we have a separate graph because there, see, I have shown this now. You started with A, then you came back to A after
You came back to A after
uh,
going through like
D.
places.
Hmm. So your internal as well as enthalpy is going to be zero. There is no change in enthalpy or energy.
Okay,
See,
okay.
in physics, you will be talking about thermodynamic processes, and you will understand whenever you are talking about work done. The simplest formula for work done is what? Force into displacement.
Yeah.
So, your physics teacher might make a joke of it. I am pretty sure. He will, when he will be teaching you the work done thing now. Work done is basically
Mhm.
energy. So work done's
Yeah.
formula is force into displacement. So if we
Yeah.
are taking the displacement into consideration, suppose you started from your home in the morning, right? You went to your
Hmm.
school. You worked hard there, right? You played some sport, right? You did something productive. But at the end of your day, when where you are coming back
Oh,
home. So if work done is force into displacement and work done is basically energy. So if you are coming back to your home, your displacement is how much?
zero.
So have you done any work actually? The work done is zero.
No.
So why are we basically going to school or working when at the end of the day our work done is going to be zero?
Oh, huh.
You might make a joke out of it.
Then stay at home then.
Hmm. Ultimately, like no matter what you do, suppose if you even leave this planet, you might be thinking like if I started with my home and I reach a new place, then there is some displacement, right? So
Yeah.
it might be considered that I have done some work. But if you broaden your perspective, you take like you talk in terms of planetary objects. So you are still on the same planet. So again,
Yep.
your work done is zero. If you jump planets,
Zero
then
work
you are
done.
still if you jump some planets, you are now in Mars, and you are like patting your shoulder and saying, "Yeah, now I have achieved some work done. I have done something in my life." Right? If
Yeah.
you just zoom out a bit, then you are still in the same galaxy, right? And
Yeah.
solar system, you can say. Again, your work done is zero. So no matter what you do, ultimately you haven't achieved
Everything
anything.
is zero. But unless you become creative.
Hmm. You might be thinking of leaving universe, right? So that is not
Leaving
possible.
universe.
It is not possible. So again, you
Or
will
going to another galaxy or going to another
Yeah.
planet.
Wherever you go, your work done is zero. So
Or you stay in one place. I mean, if you go to like different place and never come back.
Again, you are still on planet Earth.
I'm saying never come back, never going back to Earth.
Again, you are here. You cannot leave
What
the universe.
personally I have to go there to show you?
If you achieve something in your life, then I will again ask how much is your work done. So you are going to say it is zero. So you haven't achieved anything,
Uh,
right? So if
yeah,
your physics teacher asks you the same question, so you can answer work done is zero, right? Is this clear?
yeah, yeah,
Can we move ahead? Hmm. So now we have thermodynamic processes. One is thermodynamic reversible process and irreversible process. What does the term suggest? If something is reversible, we can simply go back to the position where we have started. Reversible, right? You can reverse the
yeah.
process. But what is irreversible? The processes where
Where
you
you
cannot.
can't reverse it.
Hmm. So I have two ways to explain it. One is a bit more theory and one is simple example, right? So let us go with both of them so you can understand it better.
Give
Suppose,
me 1 minute.
hmm,
Yeah,
hmm, can we continue?
yeah.
Right. So I was talking about reversible and irreversible thermodynamic processes.
Irreversible.
Okay. So let me help you understand it. Suppose you have a container, right?
Mm-hmm.
And you are applying some external pressure.
Mm-hmm.
And inside your container, you have filled some gas. So in
Okay.
reversible processes, what you are going to observe is you are going to apply a small amount of pressure in a several interval of time, and that too small interval of time. Suppose you have placed 0.5 atmospheric pressure, right, for a few
Yeah.
seconds. You applied 0.5 atmospheric pressure for 2 seconds, then you removed it. Then again you applied the same pressure for 2 seconds, then you removed it, and you followed the cycle for several times, right? So
Mm-hmm.
as you are going through small steps, they are retraceable. You are going like 0.5 2 seconds, 0.5 2 seconds, and then again and again. So you are applying small steps, and that is making your entire process retraceable, right? So this is
Okay.
a category of reversible process. But on the other hand, suppose now you have applied a very big amount of pressure. Suppose you just started with 5 atmospheric pressure. You just applied 5 atmospheric pressure and you removed it. So now, as the pressure was huge and your system was not able to accommodate it that fast, right? So now you will
Yeah.
say your system was not able to, uh, it was not expecting that much of pressure suddenly, so it will not be able to uh, uh, make it retraceable, right?
Reverse. Yeah.
Reverse. So if you are applying 5 atmospheric pressure, your system will only be able to give you back 2 atmospheric pressure. So it is a irreversible
Is
process.
5 atmospheric pressure a big pressure?
If you compare it with 0.9 or 1,
Okay.
0.5, right? So
What is
let's
the
look into,
normal pressure we are living in?
I think 1 atmospheric pressure,
Okay.
right? So let us talk.
Then doesn't that mean irreversible process is kind of impossible?
No, no, you can see, you can apply pressure. Suppose I am putting a piston onto my system and I am forcing the pressure, external pressure.
Yeah.
So
Yeah.
we can go to 300 atmospheric pressure as well, 400 atmospheric pressure as
You
well.
need like a high advanced piston which
Huh.
never breaks
Yes. We can go
because it
even
will
to
break.
1000 atmospheric pressure. It like we have specific pistons that are durable.
Yeah.
So let us the things that we have talked about. Let us see the theory of it as well. Right. So what is written over here? So let me get you familiarized with this term. PEXT means P external opposing force. For example, see what is P external? P external is the external pressure. What is P internal? The pressure that is exerted by the gas. So in reversible process, the difference between the driving force pressure of gas and opposing force P external is infinitely small, and the process can be reversed by increasing the opposite force by infinitely small amount. So as I just told you, you are applying small amount of pressure for a few seconds, and you are waiting for your system to give you the exact pressure. Right? Suppose
Yeah.
you have applied zero point 0.5 pressure for 2 seconds, and after 2 seconds, your system is able to give you the same amount of pressure back. So now you have achieved equilibrium, right? Then you again apply the same pressure and you follow the cycle.
Yep.
In irreversible process, the difference between the driving force and the opposing force is large, and the process cannot be reversed. You can understand it with a different methodology as well. Suppose you are going to second floor through stairs, right? And your stairs
Yeah.
are like the normal stairs, where the every step is like having equal, what we call that, equal distance. The normal stairs that
Mm-hmm.
we have in our home. So they are equally distributed. So you are reaching, you can walk and you can come back by following the same steps, right? But suppose now you have a different case of stairs while you where you have a very big step. Suppose let me draw
Yeah.
it. In reversible, you are going like this. Each step is of equal distance. But in
Yeah.
irreversible, your first step will be this big and the second will be this big. So will you be able to climb that big amount of
No.
so it will make it difficult. So you it is non-retraceable. But here you can go back. Right. The
Yeah.
second point. Since the reversible process is
Oh,
ex-
it's because you cannot climb that far, so you need to like extend your leg
Mhm.
to climb it, and that's not reversible.
Something like that, right?
Yeah.
I have a different example where we'll be dealing with stones, right? So let us talk this
Mm-hmm.
more scientific example, then we will go with the more generic one. So the next point is since the reversible process is extremely slow due to very small what we have written here, small difference between the driving and opposing force, it takes infinite time for completion. See, in reversible process, you are using very small interval of small intervals for a very longer period of time. So it is very slow process, right? You will
Yeah.
put zero point 0.5 again, you will do it for several times, and it is a very slow process. And the process
Yeah.
takes infinite time to complete. And for the irreversible, since the process is rapid due to the large difference between driving force and opposing force, it is completed in definite time.
But they can do it by using hydraulic pressure, right?
We can use that as well. Since the process is extremely slow, the system is in temperature and pressure equilibrium with the surrounding. For the irreversible, the process is rapid, and so the system is not in temperature and pressure equilibrium with surrounding. The reversible process takes place in a large number of infinitely small steps. Irreversible, it takes place in single step. You will just put a high amount of pressure and you will remove it. So it is a single step type of thing. The fifth point of reversible, it is not real, but an imaginary process. Why it is imaginary? Because it takes infinite time to complete and you have to involve very large number of
Which
steps.
one is
So
imaginary?
the reversible,
Irreversible.
the reversible, irreversible is the real one.
Rever- Reversible is imaginary.
Yes, because you have to use several intervals and the time that you are going to observe. or need is infinite.
What do you mean several intervals?
Suppose this is my small thing, right? This is my small earbuds basically.
Okay.
I will be needing so many number of these earbuds, and it would take me infinite time to complete my reaction. So we consider it as imaginary process. Reversible is sort of imaginary process.
So won't it be reversible by just doing like once?
No, it won't be considered as reversible. The condition for reversible is that the process should be retraceable. To For it to be retraceable, you have to take definite and specific amount of intervals. If you are starting with 0.5 for 2 seconds, you have to go with it for like
Infinite time.
again an infinite number of time. No, infinite number of steps, or you can say intervals, and it would take infinite time.
Oh, you're saying like gradually coming to a
Ah,
high pressure
you will have to do it again and again.
with the small steps.
Small steps.
It's like the smallest step, then the last step is the biggest step.
No. All will be of same magnitude.
Okay. Yeah, I think I can understand. Yeah,
Uh,
I
I
understand. I understand.
I will be taking a more simple example. See, I have written it. To write in exam, take the points from here. If they are asking you in the exam, then you can take the points from here. To understand, you can refer this. It is a more easier way to understand it, right?
Yeah.
Suppose this is your assembly, this is your system. We have a piston, and we are putting
Mm.
stones. We are putting very small stones. Are you able to
Mm.
see these circles? These are stones.
Yeah, 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 yeah.
Small pebbles, stones. Basically, we are putting some force onto it. So it will take infinite number of steps. To make it reversible, we have to put infinite number of steps. We will be needing infinite number of those pebbles, right? And it is
Okay.
going to be a very slow process, and it is
Yeah.
practically not possible, right?
Yes.
Uh,
But the thing is, it won't be infinite. It would be a lot of steps, but won't be infinite though.
See, it is going to be infinite because the condition is that we have to do this for like the entire process should take infinite time. So if the time is going to be infinite, then you won't be able to complete it at any time, right? So you will be
Should
needing
it be
infinite number of
always
pebbles.
0.9 atmospheric pressure?
No. The condition is not like it should be specific, but if you are starting with 0.9, you have to continue with it.
And what if I start with 2?
See, if you are starting with 2, then it would not behave as a ideal reversible case because now the pressure has some definite amount of magnitude, right? So you have to start with small. So let me complete this. So I think your doubts that you are having in your mind now would be clear. Let us use some Urdu as well. See, you have to
Yeah.
increase the pressure धीरे धीरे, right? Slowly.
Yeah.
Uh, एक second. Suppose आप you uh you place the small stone, right? You place a छोटा सा
Yeah.
small stone and you weight
Same
it.
size, same radius,
हाँ
same volume.
हाँ छोटा सा आपने स्टोन डाला. आपने वेट किया कि जो आपका
Mm.
इक्विलिब्रियम आ जाए, जो आपका सिस्टम है ना वो इक्वल प्रेशर दे दे. पी जो एक्सटर्नल है स्टोन के साइड से एंड जो प्रेशर लग रहा है आपका गैस इससे वो सेम हो जाए. आपको वेट करना पड़ेगा. एक पत्थर डाला, आपने वेट कर रहे हो, बैठ गए. ठीक है, कुछ टाइम में हो गया,
Okay,
फिर आपने
okay,
दूसरा
okay.
पत्थर डाला, फिर बैठ गए आप.
Mm-hmm.
फिर आपने तीसरा डाला. ऐसे कर करके आपको पत्थर डालते जाने. तो ये है ना दिमाग खराब करने वाला सर प्रोसेस पूरा का पूरा. अब यहाँ पे
Oh,
फायदा क्या होता है? सी, इफ यू आर रिमूविंग दैट स्मॉल स्टोन, then it is now retraceable. You can remove that stone. Now you have again you can if you are removing the stone, you will have to follow the same process. You will remove the
yeah.
stone, then you will wait for the pressure to get to attain equilibrium. Then you will again remove another stone. So it is retraceable, but it is very hectic.
Tick. Okay, okay. Yeah, I understand. But just one more doubt.
Hmm.
Is there a max?
No, there is no max
There's no
for
max
reversible
pressure.
because the time is infinite. You will be
Okay,
doing it,
now I understand. Now I understand. Yeah. Yeah.
but for
So
this,
since there's no max, it is impossible.
see, let us see more of it. आपने सी आपको एक पत्थर डालने के बाद ना वेट करना पड़ेगा किस चीज का, when your
Mm,
p external is equal to p internal, then again
mm,
you have to follow the same process for infinite time. स्टोन निकालने पर, राइट, दिस काइंड ऑफ थिंग। तो आई हैव रिटन इट इन उर्दू। थोड़ा 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 प्रेशर बढ़ेगा, इक्वल आया, फिर और बढ़ाया, फिर इक्विलिब्रियम आया, बहुत बार किया, फिर वापस प्रेशर कम किया थोड़ा थोड़ा। सो दिस इज अ वेरी सीरियस टास्क, बट इट इज रिट्रेसेबल though.
yeah.
Here
It's
both p
understandable.
external and p internal are small and nearly same. So for this is very important. I am going to use this sum, so keep this in mind. P external
What
is
is
equal
that?
to
Oh, okay. Approximately equal.
P external is equal to P of gas, that means P internal. They are nearly same for reversible only. Now let us talk about irreversible. See, now irreversible means what you are doing is you have taken a big stone, right? A very huge boulder you can say, and you have placed it on your piston. Now is your piston is going to move slowly or it will just collapse? It will
Which one?
see if you have rather than taking those pebbles, you have taken a boulder,
Uh-huh.
a very big stone,
Uh-huh.
and you have
Uh-huh.
placed it on your piston. Now your piston is going to collapse or it is going again like it will try to go like the previous case, slowly, like धीरे धीरे नीचे आएगा या फिर
It
एकदम
will collapse.
collapse, right? The moment you
Yeah.
remove now, the moment you will try to remove your boulder now, then your system won't be able to react exactly the way it was compressed. So now the P external, the P external is greater than P internal. The pressure that you applied
Yeah.
externally is very higher if you compare it with P internal. But once you try to remove your boulder, now the gases that were compressed, now the gas particles are very close to each other. They are forcefully, uh, like they are forced to come close to each other, and due to the electrons, they are repelling. The moment you remove that boulder, they will try to move away from each other. So that moment, your piston will move up again.
Yeah.
So now you will say the P internal is greater than P external. So I have written it in Urdu as well. जब आपने स्टोन डाला तो प्रेशर एक्सटर्नल ज्यादा था, तो उसकी वजह से क्या हुआ, कंप्रेशन। when you when you transfer when you like what do you say, when you place your big boulder on your piston, it compressed suddenly, so
Mm-hmm.
your P external was greater. But when you tried to remove it, then you observed expansion. Now your piston tried to move up. So the reason was P internal was greater. जब stone हटाया retrace करने के लिए, right? So pressure is constant throughout. If you are applying what you can say 5 atmospheric pressure due to the boulder, it was constant throughout. Your boulder is same because if you have placed the boulder, the size and mass is going to be same, and the pressure that is going to exert is again going to be same. So pressure is constant. एक ही कांस्टेंट प्रेशर से दबाया, इधर कंप्रेस मारा, ऑन द अदर हैंड वहाँ थोड़ा लगाया, okay?
Yeah, I
So
understand the whole thing.
okay. If you understood it, then it is very good. Okay. Pressure is not constant throughout. So pressure is not constant throughout here, but the pressure is constant there.
Since I was little, I always believed that if we put water in a big container and apply a lot of pressure under like a piston or something,
Mm.
if we like a syringe, if we put a water in that room and
Mm.
apply a lot of pressure due to pistons, I believe that it would turn into a solid. I always believed that.
You are saying that if you somehow push the water molecule so close that they will convert into something solid, right? You
Solid.
are saying something like that. It won't
Yeah.
work like that because you cannot do that. Now you must have known the reason, or do you have still doubt about it?
I mean, I understood. Yeah, I understood. Yeah.
Hmm. So let me think about like if I can use some example to. Okay, let me just give me few seconds. Okay. It is self-explanatory. You don't have to think too much about it. Right. So is the reversible and irreversible process clear?
Yeah.
So
Yeah.
the main question is, you were saying something like while we were talking about reversible process, you had a doubt. You were asking me like if I started with 0.5, should it is really necessary to continue the zero point 0.5 pressure? You asked something like that, right?
Um. Yeah, and I got
No,
my answer. It should be the
no,
same.
no. See, it should be the same, but the slight variations are like you can do the slight variation. Suppose you started with 0.5 and you went for
Mm-hmm.
0.6. So this small amount of variation is acceptable. But you cannot go like you started with 0.5 and the next time you are applying 2 atmospheric pressure. So small changes are
Okay.
like acceptable, but not very large variation, right? Can we move ahead?
Yeah.
Okay, just give me a few seconds. Some note somewhere the points that these 2 points. For reversible, P external is equal to P internal. That means gas.
Won't it be in the notes?
It will be in the notes, but please make like note it somewhere in your copy so you can remember it because the PDF is slightly big. So if you have
Yeah. Go back. Go back. Go back. Which one? Which one?
for reversible, the P external is equal to P internal. That P internal is basically P gas. Now, okay, let us talk about how we are going to use our reversible and irreversible process in terms of work done, right? So basically, W is our work done. And see, I told you the formula for work done is force into displacement. You might be wondering how we are getting this PdV, or do you know how we are getting it?
Just um. I don't know.
Hmm. So we can modify this formula, force into displacement into pressure into volume. How? Let us see.
Yeah.
What is pressure? Pressure is nothing but force per unit area.
Yeah.
So can I write force is equal to pressure into area? Can I
Yeah.
replace force by pressure into area into displacement? Can I write it like this?
Yeah. Sure.
What is the SI unit of pressure? Meter square. What is the SI unit of displacement? Meter.
Oh.
If you combine these two,
Oh, okay. 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 Okay.
you are going to get meter cube, and meter cube is the SI unit for volume. So if you multiply area by displacement, you will get volume. So you can write work done
Okay.
as pressure into volume. It is just derived from your force into displacement.
Okay. Okay. Yeah. I understood.
But if you are using this delta, what does it mean? This means small amount of change in volume.
Yeah.
So basically, you are trying to measure what is the small amount of change in volume while you are exerting some pressure onto it. Is it making sense?
Yeah.
So again, you have two types of work done, reversible and irreversible. So as we talked about, when we are talking about reversible process, what do we have? P external is equal to P gas,
Yeah.
and your P gas is what? Internal pressure. Inside your system, what do we have? Inside our system, we have gases. And the pressure that is exerted by gas, we call it P gas. And as the system, as the gas is inside our system, we will call it P internal, opposite of external. Suppose
The gas outside the system, it's P external, and the gas inside the system is P internal.
You can say that. See, suppose this is my system. I am placing, I have a container, and inside that container, I have some gas particles, right? And this is my
Yeah,
piston. I am applying some pressure through the piston to this gas, right? And I'm compressing this gas. So the P external is what? P external is due to the piston or not? But
yeah,
while I am putting that external pressure, what I'm observing, the gas molecules are getting compressed. They are coming close to each other,
yeah.
and that they will
So
reach a
P
point.
internal will increase.
P internal relaxing is good because now the gas molecules, as they are coming close to each other, they will repel them. They will repel themselves, and that will create
Yeah,
a pressure due to the gas that we will call Px internal, right?
yeah,
So the work done formula we just derived P dV. So we know P external is this minus P external dV we can say. And what we also know, if the process is reversible, we can use P external. We can replace P external with P gas. So we can write it like
yeah.
this and we can write it like this. So this is our formula of work done for reversible process. And you should
Okay.
remember PV is equal to nRT. This is the formula for pressure like ideal gases. PV is equal to nRT. So we are going to use this in numerical. So you should remember, you can replace this P with this. Why we have a question for you.
Yeah,
As I mentioned, this is the formula for ideal gases.
yeah,
So when we can apply this formula, when we are talking about the pressure of gas. And what is the pressure of gas? Pressure internal. As in reversible, as in reversible process, the P external is equal to P gas. We can use
mhm,
this formula. But for irreversible processes where P external is not equal to, sorry, P internal is not equal to P external, that P external is constant. So we cannot use this formula. We cannot use PV is equal to nRT formula here because here the P external is not equal to P internal because the pressure that is observed here is due to the piston only, and for piston we cannot use the gas formula. Is it making sense?
yeah. Kinda.
It won't work with that kind of, right? It is thermodynamics. You won't understand the latter part if you are not
Yeah,
able to understand. See, let us use Urdu because I think it I might be able to explain it better in that. See, uh, uh, जब रिवर्सिबल प्रोसेस राइट,
yeah.
तो जो आप बाहर से पिस्टन लगा रहे हो राइट, तो
Mm.
पिस्टन का प्रेशर इज पिस्टन का प्रेशर, बट उस पिस्टन की प्रेशर की वजह से आपकी जो गैसेज है वो कंप्रेस हो रही है, तो नाउ योर गैसेज आर आल्सो गोइंग टू एक्सर्ट सम प्रेशर और नॉट.
Yeah,
So these two are different things. The P external is due to piston and P internal is due to gas. And the formula for work done is minus PdV. So we need pressure.
yeah.
So if we are talking about reversible process, we can interconvert the external with the gas one. And how it is beneficial for me? Because the moment I exchange my P external with P gas, I can use this formula.
Oh, okay,
Uh,
okay, okay.
But if I am talking about irreversible process, here the P external is
Mhm.
constant. This is constant. So यहाँ
Yeah.
पर हमारा जो P पिस्टन है ना, पिस्टन उसका जो प्रेशर है वो
Mm-hmm.
गैस के प्रेशर के बराबर नहीं है. So if I'm talking about the external pressure, I cannot replace it with P internal. If I'm not able to exchange it with P internal, I cannot use the P gas formula. I cannot use this formula, right? So this is
Why?
because I'm not talking about the gas here because the P external is not equal to the P internal,
Uh,
P gas.
oh, okay, okay, okay. Because P internal doesn't listen to the P external.
External because it is an irreversible process. If it is
Yeah.
not talking about gas, then we cannot use the gas formula. So this is the entire thing about it. And it is very important because in your question, they might mention like this is a reversible case. So you can use this formula. It will make things easier for you. But if they are saying the process is irreversible, then you won't be able to use this formula, right?